Today, the quantization of orbital angular momentum and what it means for you. We have been talking for some time about how quantum mechanics imposes kind of an integral constraint on observable reality. Specifically, we've explored how h, Planck's constant, sets kind of a finite resolution for the information carrying capacity of space and time. The two concrete examples that we've seen from this include photons, the fundamental unit of the electromagnetic field, a smallest possible energy associated to light waves. We learned that photons, these indivisible packets of energy, necessarily come with energy inversely proportional to the wavelength of that light. And the constant of proportionality is, of course, h times c, the speed of light. Given any light wave whatsoever of a specific wavelength lambda, the energy of that light wave is necessarily an integer number of this unit hc over lambda. The second concrete example that we saw were atoms, specifically electrons moving around in their configuration in an atom, and we've learned that those electrons give off energy in the form of photons at specific energy levels distinct to the atom itself. For the case of hydrogen, we learned that these energy levels look something like minus 13.6 electron volts over n squared, where n is an integer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. Y minus is just a convention. If we add energy to the system, it becomes less and less negative. And for example, minus 13.6 over n squared, so as n increases, the size of that negative number gets closer and closer to 0. Today, we're going to be looking at a third example of how h imposes some integral constraints on observable reality. Specifically, we're going to talk about angular momentum. We've been using the constants h and c because they multiplied together equal 1240 electron volt nanometers, which is an easy number to remember, especially when we're talking about photons. But since we've had so much exposure now to these constants, let's take a look at just h by itself properly. 6.626 times 10 to the minus 34 joules seconds. It's a complicated number to ingest on its own, but if we think about it, it's got units of energy times time. And amongst the other types of physical observables that have units of energy times time, we have angular momentum. R cross p, where r is position vector, p is a momentum vector. Angular momentum is a measure of how fast things are rotating, how fast things are orbiting, how fast things are spinning, and it also kind of quantifies how hard it is to get an object like that up to speed. Mathematically, we say, r cross p, which is to say that angular momentum vector, in this case, say L, has a magnitude that's given by the magnitude of the distance, the magnitude of the momentum, and the sine of the angle between them. So really what it does is it quantifies for us kind of how the direction of a given object is changing in time. And usually, for all intents and purposes, at least for here, it's a question of orbiting, it's a question of spinning. Now, angular momentum is a deep topic, and we can talk about it for hours, but I will restrict this discussion to what we're going to be using in our early studies of quantum mechanics. So specifically, we will be concerned with two kinds of angular momentum. The orbital angular momentum associated to things like electrons moving around in an atom, very similar to how, for example, the moon orbits the Earth. And spin angular momentum, which is more intrinsic, which is more how an object is spinning about itself. Today, we are going to focus specifically on orbital angular momentum. Because h has units of angular momentum, it might not surprise you to learn that h kind of represents the smallest possible unit of angular momentum that's observable in the universe. Obviously, the smallest amount of angular momentum that an electron can have is going to be 0. But what is interesting is that we observe that angular momentum is quantized in units of h. Specifically, it is quantized in units of h over 2 pi. That 2 pi factor might be intuitive, so we're allowing h units of angular momentum per 2 pi radians of revolution. So observationally, we can see 0 units of angular momentum, 1 unit of h over 2 pi radians, 2h per 2 pi radians, 3h per 2 pi radians, 4h per 2 pi radians. These are the quantized values of angular momentum that we're allowed to observe. For the specific case of an electron orbiting an atom, these quantized values have a specific name that chemists give them, and they call them orbitals. So for n equals 0, we have s orbitals. For n equals 1, we have p orbitals, and d orbitals for n equals 2, and f orbitals for n equals 3, and so on and so forth. Why angular momentum is quantized in these units is an interesting question that we will definitely get to, but for now, I think it's probably more important to explain some of the physical consequences of the fact that angular momentum is quantized. Angular momentum is a vector quantity. We know that it's related to r cross p. What that cross means is that, yes, the magnitude is r p sine theta, but the direction is related to kind of the axis about which that rotation is taking place. So for the case of, say, the moon orbiting the Earth, the axis of rotation is obviously the plane normal to the plane at which the moon is orbiting. In short, angular momentum has a vectorial direction to it. And so when we measure angular momentum, specifically of a particle subject to quantum mechanics, we have to be cognizant of both its magnitude and its direction. And as we'll see now, h quantizes, h sets a fundamental restriction, a finite resolution, if you like, on the types of information that we can get from a quantum particle. So we already know that the magnitude is quantized. We just mentioned that. So in other words, it's nh over 2 pi. But what's also interesting is that the direction is also similarly constrained. What do I mean? When we measure angular momentum of a given particle, we will typically be using it with some kind of device. And that device will typically measure the direction of the angular momentum specific to some orientation. So for example, we may be throwing some atoms at a detector, and it may attempt to measure the angular momentum, but it's only going to measure that angular momentum in, say, the x direction, parallel to the ground, say. That means that we'll be measuring the projection of the actual angular momentum, that actual direction, that actual vector, along the x direction, which means that we're not measuring all of it all at once. We're just measuring, if you like, the x component of the angular momentum. What quantum mechanics says is any measurement that we make whatsoever of angular momentum, however you want to project it, in whatever direction you want to project it, we must observe it in integral units of h over 2 pi. In other words, the x component of angular momentum, if we are to measure it, will be also nh over 2 pi. The thing that is different here is that that integer n is going to be less than or equal to the total n, the maximum value of n, that corresponds, if you like, to the angular momentum, the magnitude of the total angular momentum of that particle. Did you catch that? We can measure angular momentum of a particle projected along a direction, and the values that are allowed are basically anything from the maximum, the total magnitude, and then any integer amount from nh over 2 pi down to 0, down to minus nh over 2 pi. And that has a very curious implication for specifically measuring the angle, the direction itself. When we measure the projection of the angular momentum along some direction specified, say, by our detector, what we're actually doing is measuring the magnitude of that angular momentum, this n max, if you like, times h over 2 pi, times cosine of the angle that's between the actual angular momentum vector, between the normal of that orbit and the direction specified by the detector. And so really what we're measuring is n max h over 2 pi times cosine theta. Now, quantum mechanics tells us that we can only measure integral units of h over 2 pi. And so this presents us with an equation for an observable set of angles that we're allowed to measure, essentially. And that is n max h over 2 pi cosine theta must equal some other integer n times h over 2 pi. So we can simplify this expression to get a relationship between cosine theta on the one hand and the ratio n divided by n max on the other. And as you can see, since n must be an integer that's between minus n max and plus n max, this restricts us to a specific set of angles that we can physically measure. Notable right away is the fact that if n max, if the magnitude of the total angular momentum of whatever it is that we're trying to measure, say an atom, an electron orbiting in an atom, if it's really, really high, if n max is really, really, really large, then we have a lot of options that we can go through. In other words, the resolution that we're allowed to measure physically through the detector, the number of angles that we can measure, is very large as well. And so this kind of gives our intuitive sense of what classical mechanics means. So in classical physics, n is a tremendous large number, 10 to the 30, something like that. So it's incredibly huge. And so there are more angles available to our system than we could ever hope to measure. But when it comes down to quantum mechanics systems, n is typically really, really small, and max is, maybe 3 or 2. So this heavily restricts the types of measurements that we're allowed to make. So let's take a look at some examples. For the case of the s orbitals, n is equal to 0, so there's no angular momentum, so there's really nothing to say. For p orbitals, we have n max is equal to 1, so that means that the allowed values of the integer n are plus or minus 1, and of course 0. And so this gives us 3 separate angles that we can measure. We can measure the angle corresponding to arc cos of 1, arc cos of 0, and arc cos of minus 1, which correspond to the different angles of 0 degrees, 90 degrees, and 180 degrees, respectively. For the d orbitals, where n is equal to 2, that gives us 5 separate angles that we can measure, right? Because n max is 2, so n can be equal to minus 2, minus 1, 0, 1, or 2. And this gives us another set of angles. These angles are 0 degrees, 60 degrees, 90 degrees, 120 degrees, and 180 degrees, respectively. Now, you can keep going, and you can do like the f orbitals, for example, and the angles, the ratios just aren't as nice, but you can still get 2n plus 1, or 2n max plus 1 distinct angles that you're allowed to observe, depending upon the direction of your detector relative to the rotating system in question. In summary, not only does quantum mechanics restrict the angular momentum of objects, the spin, the orbital motion of objects, to be quantized in units of h over 2 pi, it also restricts the types of observations that can be made. In other words, we can only ever see even the projection of that angular momentum vector along some direction must also be quantized in this fashion. And as we've seen, this has a really interesting relation to the resolving power of any experiment that can be made, insofar as that h, this quantum of angular momentum, also quantizes the resolution at which the angles of our observations of that angular momentum can be made. So you might ask, well, what if the actual angle of our spinning system, of our hydrogen atom, say, or I guess hydrogen's a bad example, our actual of our electron orbiting in an atom, say, what if that actual angle is not one of those integral units? Which one does it pick? And this takes us back to our discussion of photon polarization, where you think about that odd photon out. Does it go through the polarization filter, or does it bounce back? What does that odd photon out do when it has a 50-50 chance in front of it? Well, it flips a coin. Similarly, when we have to observe the projection of angular momentum down onto some direction, and that is not a perfect integer projection, right? What we're going to end up doing is seeing one of these options, and the option that is chosen is going to be chosen statistically. And we'll get into the details of that in due course. But suffice it to say that if you were to perform an enormous amount of measurements of precisely the same system, that is, precisely the same atom moving at precisely the same angle at precisely the same detector, if you had enormous numbers of observations, what you would find is, while the individual measurements would all be subject to those integral requirements, to those specific angles that we can measure, the average over all of the observations that we would make would actually reflect what the actual orientation of those atoms really is. In other words, once again, quantum mechanics works probabilistically. There's exercises in the show notes that are linked below. Please try them out to make sure that you understand everything that's going on. Next time, we are going to be discussing spin angular momentum, and there are some similarities, of course, to what we just discussed, but there's a few differences. There's a few extra features that we have to cover, which is why it gets its own episode. So do stay tuned for that. Thank you so much for watching. See you then.